deduce the relation that is mu2 by v minus mu1 by u is equal to mu2 minus mu1 divided by r, where refraction of light takes place from a rarer medium to denser medium through a convex refracting surface, provided refraction of light takes place from rarer to denser medium through a convex refracting surface, provided mu2 greater than mu1, in case of a convex refracting surface. Deduce the relation that is mu2 by v minus mu1 by u equal mu2 minus mu1 divided by r when refraction of light takes place from rarer to denser medium, provided mu2 greater than mu1 in case of a convex surface. And this is a convex surface, xpy be the convex surface and O be a object point, and we can denote the center of curvature of the convex surface xpy. C is the center of curvature of the convex refracting surface xpy. O is the object point. Which is situated at a distance u from the pole P of the convex surface. A ray of light will be traveling from the point O towards the convex surface xpy, and this ray of light will be incident at the point A. Now we can draw a normal NC at the point of incidence A. This is the normal NC is the normal at the point of incidence A. Incident ray OA makes an angle I, and I is the angle of incidence, and we can denote the direction along which refracted ray will be traveling in the denser medium enclosed by the convex surface xpy, and the refracted ray will form an image I on the principal axis PC. I is the image formed by the refracted ray AI, in the denser medium. The refracted ray AI makes an angle R with the normal NC, and R is the angle of refraction. We can draw a normal from the point of incidence A on the principal axis. That means AM is the normal drawn from the point of incidence A on the principal axis OI, and alpha is the angle subtended by the incident ray OA with the principal axis, and we can denote the angle beta which is subtended by the refracted ray with the principal axis, and also we can denote the angle subtended by the normal N prime C or AC with the principal axis, that is gamma. P is the pole of the convex refracting surface. And also we can denote the object distance. U is the object distance of the object point O from the pole P, and we can denote the radius of curvature R. R is the radius of curvature, and V is the distance of image I from the pole P. C is the center of curvature of the convex surface xpy enclosing the denser medium. Now we can denote the image distance V. In this case, distance of the image I from the pole P is the image distance. Here V is the image distance from the pole of the surface, and here we can denote object distance, image distance, and radius of curvature. U is EO, which is object distance from the pole of the convex surface. U is equal to PO, which is the object distance, and V is equal to PI. V is equal to PI, which is image distance V is equal to pi, that is the distance of image I from the pole P. That means V equal pi, which is the image distance of the image I from the pole P of the refracting convex surface xpy, and R is equal to Pc. R is equal to Pc, that is the radius of curvature. I is equal to Pc. R is equal to Pc, which is the radius of curvature of the refracting convex surface xpy enclosing the denser medium of refractive index mu2. A ray of light from the object point O, a ray of light from the object point O, existing on the principal axis of the convex surface xpy, existing in rarer medium of refractive index mu1. A ray of light from the object O existing in rarer medium of refractive index mu1 on the principal axis. In this case, the object point O exists on the principal axis PO of a refracting convex surface xpy, refracting convex surface xpy enclosing refracting convex surface xpy enclosing a denser medium of refractive index mu2, a denser medium of refractive index mu2. Refractive index, a denser medium of refractive index mu2 is incident at the point of incidence A on the refracting convex surface xpy, is incident at the point A on the convex surface xpy which encloses the denser medium at an angle of incidence, at the angle of incidence I, and refracted through the convex surface xpy into the denser medium, refracted through the convex surface xpy along AI in the denser medium of refractive index mu2 at the angle of refraction R, Now a ray of light from the object point O is traveling along OA and it is incident at the point A on the convex surface making angle of incidence I, and refracted ray will be traveling along AI making angle of refraction R. The refracted ray AI from the point of incidence A on the refracting convex surface xpy. The refracted ray AY with respect to the incident ray OA, at the angle of incidence I, on the refracting convex surface xpy enclosing a denser medium of refractive index mu2, on the refracting convex surface xpy enclosing a denser medium, the denser medium of refractive index mu2, and another refracted ray pi, and this refracted ray pi is with respect to the incident ray OP for normal incidence on the convex surface xpy. Another refracted ray pi with respect to incident ray OP for normal incidence, on the refracting convex surface xpy, for normal incidence on the refracting convex surface xpy. The refracted ray AI and another refracted ray PI will meet at the point I. the two refracted rays AI and PI will meet at the point I on the principal axis OC of the refracting surface, and a real image under bracket I, and a real image under bracket I is formed on the principal axis. The refracted ray AI, and another refracted ray PI will form real image I on the principal axis. Now alpha, beta and gamma be the angles subtended by. Now alpha, beta and gamma are the angles subtended by the incident ray. Alpha, beta and gamma the angles made by the incident ray OA, refracted ray AI and the radius of curvature AC, which is equal to capital R, with the principal axis OPI, OPI of the refracting convex surface XPY enclosing a denser medium. Principal axis OPI of the refracting convex surface XPY enclosing the denser medium of refractive index mu2, from the rarer medium of refractive index the refractive index mu1. Alpha, beta, gamma are the angles subtended by the incident ray, refracted ray, and radius of curvature with the principal axis. Also, a perpendicular AM, not AN, a perpendicular AM is drawn on the principal axis OPI, from the point of incidence A, capital A. Using Snell's law at the point of incidence A, we get the relative refractive index of the denser medium, with respect to the rarer medium, which is given by, using Snell's law at the point A, we get the relative refractive index of denser medium, which is 1 mu2 equals sin I by sin R. 1 mu2 is equal sin I by sin R, or mu2 divided by mu1 is equal to sin I by sin R, where mu2 is the absolute refractive index of the denser medium. Mu2 is the absolute refractive index of the denser medium, and mu1 is the absolute refractive index of the rarer medium. Mu2 by mu2 divided by mu1 is equal to sin I by sin R, where mu2 is the absolute refractive index of denser medium and mu1 is the absolute refractive index of the rarer medium. We get mu2 divided by mu1 as equal sin I by sin R. Using Snell's law at the point A, we have I and R, and we get 1 mu2 as equal sin I by sin R. Or mu2 sin R is equal to mu1 sin I. Mu2 sin R is equal mu1 into sin I. Mu2 sin R equal mu1 sin R. Mu2 sin R equal mu1 sin I, which is equation 1. If the angle of incidence I If the angle of incidence I and the angle of refraction R, under bracket R, are very small, if the angle of incidence and angle of refraction are very small, in that case sin I will be approximately equal to I and sin R will be approximately equal to R. Hence equation 1 becomes mu 2 R is equal to mu 1 I. Mu 2 R will be equal to mu 1 I, that is the equation 2, provided angle of incidence, that is I, and angle of refraction R are very small. So we get mu 2 R which will be equal to mu 1 I, which is equation 2. In the diagram is the angle of incidence, and if this angle of incidence I is very small, if this angle I is very small, that means if angle of incidence I is very small, in that case sin I is approximately equal to approximately equal to I. Similarly, angle of refraction, that is R, the angle R, if angle of refraction, that is R, is very small, if R is very small, in that case we can assume that sin R will be approximately equal to R. Sin R will be approximately equal to R. In this case, equation 1 will be converted into equation 2, that is mu 2 sin R is equal to mu 1 sin I will become mu 2 R, which will be equal to mu 1 I. Now the angle of incidence, that is I. The angle of incidence, that is I, which is an external angle, is the external angle of the triangle AOC, is equal to the sum of opposite internal angles, that is angle alpha and gamma of the triangle AOC. Therefore external angle is equal to sum of two internal angles. Therefore hence we can write I is equal to alpha plus gamma. We get the expression of angle of incidence, that is I is equal to alpha plus gamma, which is equation 2. I is equal to alpha plus gamma, which is equation 2. Similarly, the angle gamma, that is the angle subtended by radius of curvature with the principal axis, is the external angle of the triangle ACI. Hence external angle gamma is equal to sum of two internal angles, that is R and beta. So we get gamma as equal to R plus beta. Therefore R is equal to gamma minus beta. R is the angle of refraction, that is R is equal to gamma minus beta. R is equal to gamma minus beta, and that is angle of refraction, and we get angle of incidence I as alpha plus gamma. I is equal to alpha plus gamma, that is the angle of incidence, I is equal to alpha plus gamma, that is the angle of incidence. Similarly, R is equal to gamma minus beta, which is the angle of incidence. In diagram, I is the external angle of the triangle AOC, and this I will be sum of alpha and gamma. That's why we can write external angle I is equal to alpha plus gamma. Similarly, here from the triangle ACI, gamma is the external angle which will be sum of two opposite internal angles. That's why we get gamma as equal R plus beta. We get I as equal alpha plus gamma, and the angle of refraction R as equal gamma minus beta. Using the expression of I and R, using the expression of, or using this expression, that is the expression of angle of incidence I and angle of refraction R in equation 2. In equation 2 we get mu2 into gamma minus beta, mu2 into gamma minus beta, which will be equal to mu1 into alpha plus gamma. Mu2 into gamma minus beta, that will be equal to mu1 into alpha plus gamma, that is the equation 3, and here I is equal to alpha plus gamma and the expression R, which is gamma minus beta. Putting these expressions in equation 2, we get the equation 3, that is mu2 into gamma minus beta, which will be equal to mu1 into alpha plus gamma, that is the equation 3. Now the angle is always equal to length of arc divided by radius. Angle is equal to length of arc divided by radius. Any angle is equal to length of arc divided by radius. That's why the angle alpha can be written as AM divided by MO. AM divided by MO. AM is the length of arc, and beta, similarly beta is equal to AM divided by MI. AM divided by MI, not IM. And gamma can be written as AM divided by MC. Gamma can be written as AM divided by MC, where AM is the perpendicular drawn from the point of incidence I on the principal axis. This angle alpha, now angle alpha subtended by the incident ray OA with the principal axis, can be written as AM. AM is the length of arc divided by radius will be MO, not OM, because all the distance should be measured from the refracting surface. That's why MO is the distance of the object point O from the point M, and that's why alpha is written as AM divided by MO, not OM, because all the distance should be measured from the pole or from with respect to the refracting convex surface. Using these expressions in equation 3, we get, using these expressions of alpha, beta and gamma in equation 3, we get mu2 into AM by MC minus AM divided by MI is equal to mu1 under bracket AM divided by MO plus AM divided by MC. So we get this expression, that is mu2 into AM by MC minus AM by MI is equal to mu1 into AM by MO plus AM by MC, which is equation 4, which is the equation 4. As the aperture, that is the vertical line XY, as the aperture, that is the imaginary vertical line XY of the refracting convex surface XPY. Refracting convex surface XPY is very small, as the aperture XY of the refracting convex surface XPY is very small. That's why the 2 points M, that's why the point M will be very close to the point P, that is the 2 points P and M will be very close to each other. The point M will be very close to the pole P of the refracting surface of the spherical convex surface XPY. Therefore, in place of MC we can write PC, where P is the pole of the refracting surface. In place of MI we can write PI, and MO is approximately equal to PO, because the 2 points M and P are very close to each other for a small aperture of the convex surface. From equation 4 we can write mu2 into AM divided by PC minus AM divided by PI, which will be equal to mu1 into AM divided by PO plus AM divided by PC, or comma mu1 under bracket 1 by PC minus 1 by PI will be equal to mu1 1 by PO plus 1 by PC. In this case, the perpendicular AM will be cancelled out, and we get mu1 into 1 by PC minus 1 by PI will be equal to mu1 into 1 by PO minus 1 by PO plus 1 by PC, or comma mu2 by PC minus mu1 by PC is equal to mu1 by PO plus mu2 by PI, or comma mu2 by PI plus mu1 by PO is equal, we can take common PC, so here it will be equal mu2 minus mu1 divided by PC. We get mu2 by PI plus mu1 by PO, which will be equal to mu2 minus mu1 divided by PC, which is equation 5. Mu2 by Pi plus mu1 by PO is equal to mu2 minus mu1 divided by PC, which is equation 5. Now using sign convention we get PO is equal minus U, that is the object distance, and PI is equal to plus V, that is the image distance, and PC is equal to plus R, which is the radius of curvature, where U, V and R, U comma V and R are the object distance, comma image distance and radius of curvature. Image distance and radius of curvature. Now O be the object point existing on the principal axis, and object distance U is measured in the opposite direction of incident ray OA. Object distance is PO, which is equal to U, which is measured in the opposite direction of incident ray OA. That's why this object distance of the object point O from the pole P, that is object distance U, is denoted by minus U, because object distance is measured in the opposite direction of incident ray. Similarly, I is the real image formed in the denser medium, and this image distance V is measured in the same direction of incident ray. That's why V is denoted by plus V. In this case, V tends to plus V. Using sign convention, or image distance V tends to plus V, or V is denoted by plus V, and radius of curvature R is also measured in the same direction of incident ray. That's why radius of curvature is denoted by plus R. Object distance is denoted by minus U, image distance is denoted by plus V, and radius of curvature capital R is denoted by plus R. Putting the expression of object distance PO and image distance PI and radius of curvature PC, putting the expressions of PO, PI and PC in equation 5, we get mu2 divided by plus V plus mu1 divided by under bracket minus U, and is equal to mu2 minus mu1 divided by plus R. Mu2 divided by plus V plus mu1 divided by minus U is equal to mu2 minus mu1 divided by plus R. Therefore, mu2 by V minus mu1 by U is equal to mu2 minus mu1 divided by R. We get mu2 by V minus mu1 by U is equal to mu2 minus mu1 divided by R. This is the relation between image distance V, object distance U, and radius of curvature R for the image formation through a convex surface, provided the object exists in the rarer medium and real image is formed in the denser medium. Mu2 by V minus mu1 by U is equal to mu2 minus mu1 divided by R. This is the relation between the image distance V, object distance U, and radius of curvature R for the refraction of light. From an object point O existing in rarer medium through a spherical convex surface enclosing a denser medium, enclosing a denser medium of absolute refractive index mu2 from a rarer medium of absolute refractive index mu1 provided the object point O exists in the rarer medium. The object point O exists in the rarer medium of refractive index mu1, and we get mu2 by V minus mu1 by U as equal to mu2 minus mu1 divided by R. We get mu2 by V minus mu1 by U as equal mu2 minus mu1 divided by R, and here in place of this we can write refractive index of second medium under bracket mu2 divided by image distance, refractive index of second medium under bracket mu2 divided by image distance minus refractive index of and it should be refractive index of second medium under bracket mu2 divided by image distance minus refractive index of first medium under bracket mu1 divided by object distance is equal to refractive index of second medium is equal to refractive index of second medium minus under bracket mu2 minus refractive index of first medium under bracket mu1 provided the object point O exists in the rarer medium of refractive index mu1 divided by radius of curvature. This is the formula of relation between image distance, object distance, and radius of curvature for refraction of light through convex surface enclosing a denser medium, and the object point exists in rarer medium, where the first medium is the medium in which the object point O is situated, or the object point under bracket O exists. Refractive index of the first medium in this case is mu1, and the other medium should be. Now the object point O exists in rarer medium of refractive index mu1. That's why the rarer medium, in this case the rarer medium is the first medium, because the object point O exists in the rarer medium, that's why it is the first medium. And denser medium, other medium, that is the denser medium, is the second medium in which real image I is formed. In this case, refractive index of first medium, that is mu1, is used at this position in the equation, and object distance U is used in this position. And here the denser medium is the second medium. In which real image I is formed, and refractive index of second medium, that is refractive index of denser medium, mu2, is used at this position in the given relation, and image distance V is the image distance, and this image distance is used at this position, and we get refractive index of second medium. Mu2 is the refractive index of second medium, and mu1 is the absolute refractive index of the first medium. Mu2 minus mu1 divided by R means radius of curvature. And we get the required equation, that is mu2 by V minus mu1 by U will be equal to mu2 minus mu1 divided by R.